All right, so today we're going to dive into some really cutting edge stuff. We're talking about how we're pushing the limits of reasoning in large language models, those LRMs everyone's buzzing about.
Yeah, it's a fascinating area, really rapidly evolving.
Like you've got OpenAI's O1 and DeepSeek's R1. They're already doing some pretty mind-blowing stuff with complex thought processes, right?
Absolutely. And a lot of that comes down to techniques like chain of thought. Basically, it's like the model breaks down a problem step by step.
Oh, I see. So it's like mapping out a strategy before jumping in.
Exactly. And then you have long code takes this even further, allowing for much more extended and intricate lines of reasoning.
So they're not just thinking in short bursts anymore. They can really dig deep into a problem.
Precisely.
But here's the thing, and this is where it gets really interesting. As these models get better at tackling these super complicated tasks, there's a kind of a bottleneck that emerges.
Right. And it's like, they can only rely on what they already know for so long.
Yeah, so if they're purely working with their internal knowledge, it can lead to those inaccuracies, what we often call hallucinations, right?
Precisely. And on top of that, for really demanding tasks, those that involve a ton of calculations or simulations, the model's internal processing can become super inefficient.
Like, imagine trying to do some complex physics simulation just in your head. Like, you'd hit a wall pretty quickly.
Absolutely. There's a limit to what you can process internally.
So, what's the alternative? It seems like there's this really promising avenue that's starting to be explored. It's called Tool Integrated Reasoning, or TIR.
Right, TIR. And it's this idea of, okay, let's not just make the model think harder internally. Let's give it access to external tools, specialized instruments that can really augment its capabilities.
Okay, so instead of trying to do everything themselves, they're learning to outsource, like delegate certain tasks,
Exactly. And a really powerful tool in this context is a code interpreter.
like Python, right? That kind of thing.
Yes, Python is a great example. It lets the model execute those complex calculations, run those simulations we were talking about, and even do self-torques on its own work.
So it's almost like having a built-in calculator and debugger, but much more powerful.
Right. It fundamentally changes the game in terms of what these models can achieve.
We've even seen hints that OpenAI's O1 might be using tools in this way, which is pretty exciting.
Definitely points towards the direction things are heading.
So this brings us to the heart of today's deep dive. We're looking at a research paper that tackles a really fundamental question. How can we combine the strength of Longcot, that intricate internal reasoning, with the reliability and power of TIR?
It's about achieving a level of reasoning that goes beyond what either approach can do on its own.
Right, like finding that sweet spot where they work together synergistically.
Exactly.
And this is where START comes in. It stands for Self-Taught Reasoner with Tools. And it's this brand new long-caught reasoning model that's designed to boost its reasoning skills by integrating external tools, especially a Python code interpreter.
So it's not just about having the tools, it's about knowing when and how to use them effectively.
And that's what makes START so innovative. It's not just equipped with tools, it's also got this self-learning framework that lets it actually learn how to use them.
And this framework is based on two key innovations, Hint-infer and Hint Rejection Sampling Fine-Tuning, or Hint-RFT.
Okay, so two really powerful techniques that enable this self-teaching process.
Right. So first, during problem solving, START uses this clever technique called Hint-infer to kind of nudge the model towards using the tools. It's like a little prompt or suggestion, but strategically placed to make the model think, oh, maybe using Python would be a good idea here. And then the second part is Hint-RFT. It takes what the model learns from these hints and uses it to actually train itself to become better at tool usage over time.
So it's kind of a two-pronged approach. First, guide the model to use the tools, and then let it learn from that experience.
Exactly. It's a really elegant solution to this challenge of teaching models to use tools effectively.
Now, before we dive into the details of these techniques, it's worth mentioning that the base model used for this research is QWQ32B Preview. And to test START's abilities, the researchers put it through a gauntlet of really tough benchmarks. We're talking about GPQA, a set of PhD-level science questions, the notoriously difficult math problems from AMC 23, AME 24, and AD 25, and the very demanding code benchmark, LiveCodeBench.
Yeah, they didn't go easy on it. They wanted to see how it stacked up against the best of the best.
And as we'll explore, the results are quite impressive. START not only keeps pace with state-of-the-art models like ART1 Distill, Quinn 32B, and O1 Preview, but in some cases it actually surpasses them. So let's break down these techniques, starting with Hint-infer. It's presented as a novel test-time scaling method. What does that actually mean?
Okay, so imagine you have an LRM, right? And it's in the inference process, meaning it's actually generating answers or solutions. Now, let's say you want to give it a little nudge, a subtle hint, especially in situations where using an external tool could be really beneficial. That's what Hint-infer does.
So it's like giving the model a little extra guidance at just the right moment.
Exactly. And the ingenious thing is, it does this without needing any explicit demonstration data. Traditionally, if you wanted to train a model to use tools, you'd have to provide it with a ton of examples of how and when to do so.
So it's kind of like learning by doing, but in this case, it's more like learning by being shown.
Right. But Hint-infer bypasses all of that. It just uses these carefully crafted prompts to activate the model's latent ability to use tools. It's almost like unlocking a hidden skill the model already possessed but didn't know how to tap into.
That's fascinating. So it's not really teaching the model something new. It's more like reminding it of something it already knows how to do.
Exactly, and that's what makes it so powerful. You can apply it to existing models without having to retrain them from scratch.
So how does this work in practice? Where do these hints actually get inserted? It seems like it could potentially disrupt the model's natural thought process.
Yeah, that's a valid concern, but the researchers found that there are a few strategic places where you can insert these hints without causing too much disruption.
So like pressure points where a little nudge can make a big difference.
Exactly. One of those places is after high frequency conjunctions. These are words like alternatively or wait, which often pop up when the model is kind of pausing to reflect or consider different options.
So it's like catching the model at a natural break in its thinking.
Exactly. And another place is right before the stop token, which is the point where the model decides, okay, I'm done with this thought. By adding a hint there, you kind of prompt the model to think a little bit longer to explore other possibilities.
I see. So it's almost like giving the model a little extra time to ponder and potentially reach for those tools.
Precisely. And this brings us to another really interesting finding, the sequential test timescaling effect.
Okay, what's that all about?
So, what they found was that if you repeatedly insert hints before the stop token, giving the model more and more opportunities to consider using tools, the probability of it arriving at the correct solution actually increases.
So the more you nudge it in the right direction, the better it performs.
It seems that way, which suggests that these LRMs have this kind of untapped potential for problem solving that can be unlocked by just giving them more processing time and gently guiding them towards the tools.
It's like if you give someone more time to work through a problem and offer some helpful suggestions along the way, they're more likely to figure it out.
Yeah, and in the context of LRMs, it might mean that we don't always need to make these models bigger and bigger. Instead, maybe we just need to find smarter ways to help them utilize their existing capabilities more effectively.
It's like giving them more thinking space, so to speak, through the potential of tool use.
Exactly.
So can you give us some concrete examples of what these hints actually look like in action?
Sure. So for math problems, sometimes a simple hint like, wait, maybe using Python here is a good idea, is enough to prompt the model to start generating code to perform calculations or check its logic.
That's pretty amazing that such a subtle prompt can have such a significant effect.
Right. And then for coding tasks, which often require more intricate reasoning and debugging, they found that they needed to use more carefully crafted hints, even templates for self-testing, to encourage the model to run its code against test cases as part of its thought process.
So the type of hint really depends on the nature of the task.
Exactly. It's not a one-size-fits-all approach.
It sounds like they've developed quite a collection of those hints.
They have, actually. They call it the Hints Library, which is a curated set of hints designed for different functionalities. For math reasoning, you have hints that encourage reflection on the solution, verification of logical steps, exploration of alternative methods. And for code-related tasks, the focus is on self-debugging. Figure 3 in the paper shows some nice examples.
Oh, I see. Like there's a debug hint that tells the model to look closely at error messages and test case failures, and a complex calculations hint designed for math problems that require a lot of number crunching.
Precisely. And what's really cool is that they've designed these hints based on their understanding of how these models think, trying to nudge them in the right direction at key moments in their reasoning process.
So how do they actually decide where to insert these hints? You mentioned those high-frequency conjunctions earlier.
Yeah, so BQ4 shows a word cloud of all the conjunctions that pop up frequently in the model's reasoning trajectories. Words like alternatively wait, they kind of act as natural inflection points, places where you can slip in a hint without disrupting the flow too much.
So it's like finding the seams in the fabric of thought and gently weaving in these prompts.
That's a great analogy.
So what impact did using Hint-infer actually have on the model's performance across those benchmarks?
Well, Table 6 in the paper shows some really compelling data. They tested the base QWQ32B preview model on AME24, AME25, GPQA, AMC23, MAH500, LiveCodeBench, and as they increased the number of hints, the model's accuracy generally went up too. It's like each hint gave it a little boost, helped it refine its reasoning a little bit further.
So more hints, more chances to use the tools, better performance overall. Makes sense.
Right. But you might remember that earlier we said that start, hint, infer didn't show as much improvement, and there's a reason for that.
Oh yeah, what was that about?
So remember how start has already gone through this fine-tuning process with Hint-RFT to learn how to use tools? Well, the researchers think that because of that, the explicit hints from hint-infer might be a bit redundant.
I see. So it's like giving extra instructions to someone who's already an expert. They might not need it as much.
Exactly. It's like you might suggest a particular knife to a novice chef, but a seasoned professional probably already knows which knife to use for the job.
That's a great analogy. So for our listeners who are all about efficiency and getting the most out of their learning, what's the key takeaway here about hint infer?
Well, it seems like it could be a really promising way to boost the reasoning power of existing LRM without having to retrain them. It's a relatively lightweight approach that could potentially unlock significant performance gains on those really tricky cognitive tasks, all by strategically nudging the model towards using external tools.
So hint infer is all about that test time guidance. Now let's switch gears and talk about the second core innovation of START, hint rejection sampling fine-tuning, or Hint-RFT. This is where the self-teaching aspect really shines through.
Absolutely. This is the process where START actually learns to become self-aware of when and how to use external tools effectively.
Okay, and it builds directly on those insights from hint infer, right?
Right. So the first step is to apply hint infer to a whole bunch of problems and generate a ton of different reasoning trajectories. Some of these trajectories will involve the model using tools because of the hints, and some won't.
So it's basically encouraging the model to demonstrate tool usage even if it wouldn't do it on its own.
Exactly. And then comes the scoring and filtering process. The researchers used rule-based scoring to evaluate which of the model's reasoning steps looked promising and led to correct solutions. Any trajectories with repetitive or nonsensical patterns were tossed out.
So they're carefully curating the data, making sure they're only keeping the good stuff.
Precisely. And then they made some specific modifications to the hints within the code data. For example, they replaced specific Python identifiers with a more general debug code template and removed any output placeholders.
Why those specific changes? What was the reasoning there?
Well, the idea was to teach the model the general principle of using a code interpreter for debugging and verification, rather than having it memorize specific code snippets or expected outputs. They wanted to give it a more abstract understanding of when and how to use tools.
So it's not just about memorizing solutions, it's about learning the underlying strategy.
Right, it's like teaching someone to fish instead of giving them a fish.
Perfect analogy. And this curated set of trajectories is what they call the seed data set, or D-seed.
Exactly, and this is where the self-teaching magic happens. They take the base model, QWQ32B preview, and fine-tune it on DSeed, which results in a new model called Start Zero. The key thing here is that Start Zero has now been exposed to all these examples of tool usage, and it's starting to get the hang of it.
So it's beginning to understand why and when it's a good idea to call in those external reinforcements.
Exactly. But the learning journey doesn't stop there. There's another stage called reinforcement learning from feedback, or LFT. In this stage, Start Zero generates its own reasoning trajectories through a process called self-distillation.
So now it's learning from its own experiences.
Exactly. It's like practicing what it's learned and getting feedback on its performance. And this self-generated data helps to build an even more diverse and robust data set called DStart. Finally, they take the base model and fine-tune it one last time on DStart, and that produces the final start model.
So it's this multi-stage process of prompting, data curation, and iterative fine-tuning, all designed to make the model a self-taught expert in tool usage.
Exactly. And figure 1 in the paper shows a nice visual overview of this whole training framework.
It's always helpful to have a visual to make sense of these complex processes. And what about the data they used to train START? How much data are we talking about, and where did it come from?
Well, for math, they used a combination of problems from past AMO competitions, the math dataset, and Numina Math, adding up to about 40,000 problems in total. And for coding, they pulled problems from Codeforces, various coding competitions, and LiveCodeBench, around 10,000 problems.
Wow, that's a lot of problems to chew on.
It is, and I also made sure to use decontamination methods to prevent overlap between the training data and the benchmarks they use for evaluation.
So it's a fair test of the model's ability to generalize to new problems. And Table 5 in the appendix breaks down the specific data sources and quantities.
Exactly.
Okay, so we've covered the foundational LRMs, those limitations of relying on internal reasoning, the emergence of TIR, and the two core innovations behind START, Hint-infer and Hint-RFT. Now for the big question, How did START actually perform on those challenging benchmarks?
Well, the main results are in Table 1, and they're pretty impressive. START achieved an accuracy of 63.6% on GPQA, 95.0% on AMC23, 66.7% on AME24, 47.1% on AME25, and 47.3% on LiveCodeBench.
Those are some solid numbers, but how do they stack up against the base model and those other state-of-the-art systems?
That's where it gets really interesting. Compared to the base QWQ32B preview, START showed significant improvements across the board. 5.5% on GPQA, 3.8% on Mass 500, a whopping 15.0% on AMC23, 16.7% on AME24, 7.1% on AME25, and 5.9% on LiveCodeBench.
So those are not just marginal gains, those are really substantial improvements.
Right, and even more impressively, START achieved performance that's comparable to, and in some cases even better than, R1 Distill Quen 32B, which is distilled from a much larger model, and even O1 preview from OpenAI.
Wow, so it's punching well above its weight class.
It really is, and it shows that this approach of integrating long caught with tool usage has some serious potential.
Now, did the researchers look at how START performed on different types of questions within those benchmarks?
They did. Table 2 breaks down START's performance on GPQIA by scientific discipline: physics, chemistry, biology. Interestingly, START did best on physics questions, while Search-O1, another strong model, excelled in biology.
That's interesting. Why do you think that is?
Well, the researchers think it has to do with the nature of the questions in each domain. Physics problems meant to involve more complex calculations, which START is really good at thanks to its Python tools. Biology questions, on the other hand, often rely more on knowledge retrieval, which might explain why Search-O1, with its access to web search, does well there.
So it highlights how tool integration is especially beneficial for certain types of reasoning tasks.
Exactly. And then around the math benchmarks, where START also showed really impressive gains, especially on Math 500, AME23, AME24, and EME25. Again, this really underscores how those Python tools can make a huge difference in tackling tough math problems.
And what about LiveCodeBench? How did START perform across the different difficulty levels there?
Table 3 shows that START's biggest improvements on LiveCodeBench were on medium difficulty problems. The researchers think this is because for easier problems, the base model was already pretty good even without tool use. And for the really hard problems, even with the enhanced debugging capabilities from the tools, the problems were just too complex.
So it's in that sweet spot of medium difficulty problems where START's ability to run code and debug itself really shines.
Exactly. Figure 2 provides a really nice case study from LiveCodeBench where the base model kind of hallucinates during the test case analysis and gets the wrong answer. START, on the other hand, uses the code interpreter to methodically debug its code and ends up solving the problem correctly.
It's great to see a concrete example of how this all works in practice. It makes it much easier to grasp.
Absolutely. And if you're interested in seeing more examples, Appendix 8.5 has a bunch of other case studies from AMT23, AME24, AME25, MFH500, and GPQIA.
Plenty of material to dig into there. Now, a question that might come to mind for our listeners is, are these improvements simply because START was trained on more data than the base model? Did the researchers address that?
They did in analysis 4.5.1. They trained another model, QWQ-RFT, on the same data as START, but without allowing any tool usage during training. The results, shown in Table 4, indicate that QWQ-RFT performed pretty much the same as the original base model.
So it wasn't just a matter of more data, it was the tool usage that made the real difference.
Exactly. That's a key point.
All right, so to wrap up our deep dive into START, what are the key takeaways?
Well, START introduces two really important innovations: Hint-infer for guiding tool usage during testing, and Hint-RFT for enabling the model to learn how to use tools effectively. And the results show that by combining long-caught reasoning with tool usage, you can achieve state-of-the-art performance on some really tough reasoning tasks.
And this makes START the first open source LRM to achieve this level of integration, right?
Right, it sets a new bar for open source LRMs and opens up a lot of exciting possibilities for future research.
Of course, no research is without its limitations. What did the authors identify as potential areas for improvement?
Well, right now, they've only focused on integrating a Python interpreter. Expanding to other tools like search engines or specialized knowledge bases could be really interesting. They also pointed out that the current method of manual hint design could be improved. Automating that process would be a big step forward.
And they also acknowledged the limited scope of the benchmarks they used and the need to test this approach on a wider range of real-world problems.
Right, and they touched on the importance of considering the ethical implications and potential risks of these powerful technologies, which is crucial as we continue to push the boundaries of AI.
So looking ahead, what are some of the most exciting research directions that this work is paving the way for?
Well, I think expanding the range of tools that can be integrated is a big one. Developing better ways for the model to decide when and how to use those tools autonomously would be huge. And of course, testing these techniques on more diverse and realistic data sets is essential.
So much potential for future exploration here.
Absolutely.
So to summarize, START is a really exciting development in the field of LRMs. Its novel self-learning framework for tool integration with Hint-infer and Hint-RFT really pushes the boundaries of what these models can do. And its impressive performance on those challenging benchmarks shows that combining deep, step-by-step reasoning with the power of external tools like Python can unlock some incredible new possibilities for tackling complex problems.
It really makes you wonder where this technology will go next.
Exactly. And for those who want to delve deeper into the technical details, the research paper is publicly available. It's referenced as 2503.04625v2.pdf.
And as we wrap up, here's a thought-provoking question for our listeners. Do you think these models will eventually learn to not only use existing tools, but also discover and integrate entirely new tools on their own?
That's a fascinating question to ponder.
It is, and it really speaks to the transformative potential of AI. Thanks for joining us on this deep dive.